What if I told you that everything you've been taught about black holes, those mysterious cosmic monsters lurking in the depths of space, is both completely true and fundamentally wrong at the same time? Picture this. Right now, at this very moment, there's a black hole at the center of our galaxy called Sagittarius A star. It's real. We photographed it. We've watched stars orbit around it for decades. In 2020, the Nobel Prize in Physics was awarded to Roger Penrose, Reinhard Genzel, and Andrea Ghez for their work proving black holes exist. But here's the twist that's going to shatter everything you think you know. The singularity, that infinitely dense point of infinite gravity that every science documentary has drilled into your brain. The thing that's supposedly sitting at the heart of every black hole, it doesn't exist. It was never real. It's a mathematical ghost, a placeholder for our ignorance. And in the next 3.5 hours, I'm going to prove it to you using the actual words of the physicists who discovered black holes, the mathematics that describe them, and the mind-bending implications of what's actually there instead. By the end of this video, you won't just understand black holes differently, you'll understand reality itself differently. Before we dive into one of the most profound mysteries in all of physics, do me a favor, smash that like button, hit subscribe, and drop a comment telling me what country you're watching from and what time it is right now. I'm genuinely curious to see how far across the globe this mind-bending journey is going to reach. Are you watching this at midnight in Tokyo? During breakfast in Berlin? Let me know. Let's start with the story you already know, because we need to understand the why before we can uncover the truth. You've heard it 1,000 times. A black hole forms when a massive star runs out of fuel and collapses under its own gravity. The collapse is so complete, so total, that all the star's mass gets crushed down into a single point of infinite density, the singularity. At this point, gravity becomes infinite. Space and time break down. The laws of physics cease to function. It's the ultimate cosmic mystery, and it sits at the heart of every black hole in the universe. Except it doesn't. Here's the first thing you need to understand. When physicists talk about a singularity, they're not describing something they've discovered. They're describing a failure. A singularity in a mathematical equation is where the equation stops working, where it spits out infinity or nonsense. It's like dividing by 0 on a calculator. You don't get a real answer. You get an error message. The singularity isn't a physical object. It's physics itself, throwing up its hands and saying, I don't know what happens here. Carl Schwarzschild discovered the first exact solution to Einstein's field equations in 1916, just months after Einstein published general relativity. Schwarzschild was literally in the German army trenches during World War I when he did this. Calculation 1 of the most profound intellectual achievements in human history, scribbled out between artillery barrages. He found something shocking. His equations predicted that if you compressed enough mass into a small enough space, you'd create a boundary in spacetime where light itself couldn't escape. We now call this the event horizon. But here's what's crucial. Schwarzschild's equations also predicted something else. At the very center, at radius 0, the equations broke down completely. Infinity appeared in the calculations. This is the so-called singularity. And Schwarzschild, being a brilliant mathematician, knew exactly what this meant. His solution was incomplete. The equations were telling him there was something they couldn't describe. Think of it like this. Imagine you're creating a map of your city. You chart every street, every building, every park. But when you get to the center of town, your measuring tools start giving you nonsense readings. Your compass spins wildly. Your GPS says you're at coordinates infinity. You wouldn't conclude that there's actually an infinite point at the center of your city. You'd conclude your tools are broken. That's what a singularity is, a broken measurement tool. Einstein himself hated singularities. In 1939, he wrote a paper trying to prove they couldn't exist in nature. He thought they were mathematical artifacts, glitches in the equations that had no physical reality. He believed that nature had to be more sensible than that. And you know what? He was probably right. But here's where the story gets interesting, where we start to peel back the layers of this cosmic onion. For decades after Schwarzschild's discovery, most physicists didn't believe black holes were real at all. They thought the event horizon itself was probably just another mathematical artifact. It wasn't until the 1960s that theoretical work by people like Roger Penrose and Stephen Hawking convinced the scientific community that event horizons, and therefore black holes, could actually exist in our universe. Penrose proved something remarkable in 1965. He showed that once an event horizon forms, general relativity predicts that a singularity must form inside it. This became known as the Penrose singularity theorem, and it earned him half of that 2020 Nobel Prize I mentioned earlier. But here's the crucial part that gets lost in translation. Penrose proved that general relativity predicts singularities. He didn't prove that singularities actually exist. He proved that our current theory of gravity, when pushed to its limits, breaks down and produces mathematical infinities. It's the difference between a map and a territory. General relativity is a map of how gravity works, and it's an extraordinarily good map, accurate to incredible precision in every situation we've tested. But Penrose showed us exactly where the map has a hole in it, where it says, "Here be dragons," and gives up trying to describe reality. Here's a question that's going to start rewiring your brain. What does it actually mean for something to be real? The event horizon is real. We know this with absolute certainty now. In 2019, the Event Horizon Telescope collaboration, a network of radio telescopes spread across the entire planet, working together as one Earth-sized detector, captured the first direct image of a black hole's event horizon. It was the supermassive black hole at the center of the galaxy M87, and the image showed exactly what general relativity predicted: a dark shadow surrounded by a bright ring of light. In 2022, they released the image of our own galaxy's central black hole, Sagittarius A star. Again, the event horizon was exactly where the mathematics said should be. These aren't artists' interpretations. These are actual photographs of the boundary beyond which light cannot escape. But here's what will blow your mind. The event horizon isn't actually a physical surface. There's nothing there. If you fell through an event horizon assuming you could somehow survive the journey, which you absolutely couldn't, we'll get to that. You wouldn't hit anything. You wouldn't feel anything. There'd be no membrane, no barrier, no surface at all. You'd just smoothly pass through a region of spacetime with a particular mathematical property. It's the point of no return. Think of it like this. Imagine you're in a boat on a river, paddling upstream. As you get closer to a waterfall, the current gets stronger. Eventually, you reach a point where the current is flowing faster than you can paddle. That's your event horizon. It's not a physical barrier. The water doesn't suddenly become solid or change in any tangible way. It's just the geometric point where the flow of the river exceeds your ability to fight against it. Once you cross that line, you're going over the falls no matter how hard you paddle. For a black hole, space-time itself is flowing inward faster than light can travel outward. The event horizon is simply where that inward flow hits the speed of light. It's a geometric property of how space-time is shaped, not a physical object. Andrea Ghez, one of those 2020 Nobel Prize winners, spent over 2 decades meticulously tracking the orbits of stars around Sagittarius A star. She documented stars moving at speeds up to 3% the speed of light, whipping around an invisible point in elliptical orbits that precisely matched what general relativity predicted for an object with 4 million times the mass of our Sun, compressed inside an event horizon with a radius of about 12 million kilometers. That's smaller than Mercury's orbit around the Sun. 4 million solar masses in a space smaller than Mercury's orbit. The event horizon is definitely there. The black hole is definitely real. But what's inside? This is where everything you think you know starts to crumble. Every science documentary has shown you the same thing. Matter falling through the event horizon, spiraling down toward the singularity at the center, eventually crashing into that infinitely dense point. It's a compelling image. It's also almost certainly wrong. Here's your first major paradigm shift. Time itself behaves so strangely near a black hole that the question, what's at the center right now, might not even have an answer. Not because we don't know, because the question itself might be meaningless. From the outside, watching something fall toward a black hole, you'd see it slow down as it approached the event horizon. This isn't an optical illusion. Time actually runs slower in strong gravitational fields, an effect called gravitational time dilation. As the falling object gets closer to the horizon, time for that object slows down more and more compared to your time. From your perspective, the object never actually crosses the event horizon. It gets dimmer and dimmer, redder and redder, slower and slower, asymptotically approaching the horizon, but never quite reaching it. You'd have to wait literally forever to see it cross. Now, here's the kicker. From the perspective of something falling in, the journey to the event horizon and beyond takes a finite amount of proper time, the time experienced by the falling object itself. But because of the time dilation, the outside universe ages infinitely fast from the falling object's perspective as it approaches the horizon. The entire future history of the external universe flashes by in a finite time. This creates a bizarre situation. Does the object ever actually reach the singularity in any meaningful sense? The answer depends on whose clock you're using, and the universe doesn't have a preferred clock. This is our first hint that the singularity might not be a real place you can actually get to, but rather a kind of mathematical mirage. Let me introduce you to one of the most brilliant minds in theoretical physics, Stephen Hawking. You know his name, but you might not know the specific discovery that's relevant here. In 1974, Hawking proved something that shocked the physics world. Black holes aren't actually black. Using quantum mechanics, the physics of the very small Hawking showed that black holes must emit radiation. The quantum vacuum near the event horizon can create particle-antiparticle pairs, and occasionally, one particle falls in while the other escapes. From the outside, this looks like the black hole is radiating particles. This is called Hawking radiation, and it means black holes slowly evaporate over time. Now, here's where this becomes relevant to our singularity problem. Hawking radiation is thermal completely random, carrying no information about what fell into the black hole. This created what became known as the black hole information paradox. The paradox goes like this. Quantum mechanics says information can never be truly destroyed. But if you throw a book into a black hole, and the black hole eventually evaporates into random radiation, where did the information in the book go? For decades, this was just a theoretical puzzle. But in the 1990s and 2000s, physicists started taking it seriously as a clue that something was fundamentally wrong with our picture of black holes. And the more they investigated, the more they realized the problem is the singularity. Here's why. If information really does fall into a singularity, an infinitely dense point where physics breaks down, then it's effectively destroyed, which violates quantum mechanics. But quantum mechanics is one of the most tested, most reliable theories in all of physics. It works. Every experiment ever done confirms it. So either quantum mechanics is wrong, unlikely, or the singularity isn't real, much more likely. Leonard Susskind, one of the pioneers of string theory, proposed something radical in the 1990s. Maybe the information never actually makes it to the singularity. Maybe it gets encoded on the event horizon itself in a kind of holographic way. This idea, called the holographic principle, suggests that all the information about what's inside a black hole is actually stored on its two-dimensional surface, like a hologram that creates a three-dimensional image. Think of it like this. Imagine you're watching a 3D movie. The screen is two-dimensional, but the image appears three-dimensional. The holographic principle suggests that reality might work the same way. What appears to be a three-dimensional interior to a black hole might actually be fully described by information encoded on the two-dimensional event horizon. If this is true, and there's mounting evidence that it is, then the singularity is even less real than we thought. It's not just a mathematical artifact. It might be completely superfluous to the physics. Everything about what falls into a black hole might be encoded on the surface, with nothing actually reaching the center at all. But wait, I can hear you asking, if the singularity isn't real, what is at the center of a black hole? What's actually there? The answer is going to require us to understand something profound about the nature of reality itself. But before we get there, let me blow your mind with something even stranger. There are different kinds of black holes, and some of them might not even have an inside in the way you think. Everything I've told you so far has been about the simplest kind of black hole, a non-rotating, uncharged Schwarzschild black hole. But real black holes in nature aren't like this. They rotate, they spin, and when a black hole spins, the geometry of spacetime inside becomes far, far stranger. In 1963, Roy Kerr found the solution to Einstein's equations for a rotating black hole. The Kerr metric, as it's called, revealed something shocking. Rotating black holes have two event horizons, not one. There's the outer event horizon, similar to the Schwarzschild case. But inside, that is an inner horizon called the Cauchy horizon. And at the center, instead of a point singularity, there's a ring singularity, a circle of infinite density. But here's where it gets really weird. According to the Kerr solution, if you could somehow survive the journey through both horizons, you could theoretically pass through the ring singularity without hitting it. And on the other side, the equations suggest you'd emerge into another region of space-time, possibly another universe. Now, before you get too excited, this almost certainly isn't actually possible. The interior of a real rotating black hole is violently unstable. The Cauchy horizon would be a place where all the light that ever fell into the black hole throughout its entire history would get blue shifted to infinite energy and create a wall of infinite energy density. This is called the blue sheet, or the mass inflation instability, discovered by physicists like Eric Poisson and Werner Israel in the 1980s and 1990s. In other words, the Cauchy horizon is itself a kind of singularity, a place where physics breaks down, and it forms before you'd ever reach the ring singularity at the center. So once again, we find that general relativity is pointing to its own limitations, showing us exactly where the theory stops working. But think about what this means. We now have multiple different places inside a black hole where the equations break down. The center isn't special. The singularity isn't this unique, inevitable endpoint. Instead, we have a whole landscape of mathematical breakdown, different regions where general relativity says, I don't know what happens here. This is a crucial clue. The singularity isn't a feature of reality. It's a bug in our description of reality. It's a sign that general relativity, as brilliant as it is incomplete. It's pointing us toward a deeper theory, a more fundamental description of how nature actually works. What we need is a theory of quantum gravity, a theory that combines general relativity's description of space-time and gravity with quantum mechanics' description of matter and energy at the smallest scales. And here's the thing. Every serious attempt at quantum gravity suggests the same conclusion. Singularities don't exist in the real quantum theory. They're smoothed out by quantum effects. Let me give you an analogy. Imagine you're looking at a coastline from an airplane. From high up, the coastline looks smooth and continuous. But as you get closer, you see it's actually made up of individual rocks and grains of sand. The smooth coastline is an approximation that works at large scales, but breaks down when you look closely. Similarly, the singularity is what you see when you look at a black hole with general relativity, a classical, non-quantum theory. But when you look with quantum eyes, you see something different. The infinite density smooths out. The breakdown of physics resolves into something finite and comprehensible. We don't have a complete theory of quantum gravity, yet that's one of the biggest unsolved problems in all of physics. But we have candidates: string theory, loop quantum gravity, and others. And remarkably, despite approaching the problem from completely different angles, they all agree on one thing: the singularity is not real. Let's talk about string theory, because it offers one of the most concrete alternatives to the singularity picture. Now, I know string theory has a controversial reputation. It's hard to test, makes predictions that are difficult to verify, and has been criticized for being more mathematics than physics. But love it or hate it, string theory has given us profound insights into the nature of black holes. In string theory, the fundamental constituents of reality aren't point particles. They're tiny, vibrating strings of energy. Different vibration modes of these strings correspond to different particles: electrons, quarks, photons, and even gravitons, the hypothetical particles that carry the gravitational force. The strings are incredibly small, about 10 to 35 meters. That's the Planck length, the shortest distance that has any meaning in quantum gravity. Now here's the key insight. In string theory, when you form a black hole, you don't get a singularity. Instead, you get what's called a fuzzball. The idea was developed by Samir Mathur and his colleagues in the early 2000s, building on earlier work by Andrew Strominger and Kamran Vafa. A fuzzball is exactly what it sounds like. Instead of all the mass crushing down to an infinitesimal point, it forms a tangled ball of strings at roughly the size of the event horizon itself. There is no interior. There is no singularity. The black hole is just a fuzzball, a complicated, quantum mechanical configuration of strings that occupies the entire volume inside the event horizon. Think of it like this. Imagine trying to stuff a bunch of springs into a box. If the springs are rigid point objects, you could theoretically compress them down to a single point. But if they're actual springs with structure and quantum properties, they'll resist compression, they'll push back, they'll tangle up with each other and form a complicated, extended structure. That's the fuzzball. The brilliant thing about the fuzzball picture is that it solves the information paradox naturally. Information doesn't get destroyed at a singularity, because there is no singularity. Instead, information gets encoded in the quantum state of all those tangled strings. As the black hole evaporates through Hawking radiation, the information slowly leaks back out, encoded in subtle correlations in the radiation. The information is preserved, just as quantum mechanics requires. Moreover, the fuzzball picture explains where Hawking radiation actually comes from. In the classical picture, Hawking radiation is created at the event horizon by quantum effects in the vacuum. But this always seemed a bit mysterious. How does the radiation know about what's inside the black hole if nothing can escape? In the fuzzball picture, the radiation comes directly from the quantum excitations of the strings that make up the fuzzball itself. It's much more natural and straightforward. Now, I should be clear. We don't have direct observational evidence for fuzzballs. We probably won't for a long time. The quantum structure would be at scales far too small to observe with any foreseeable technology. But the fuzzball picture is mathematically consistent, solves long-standing paradoxes, and arises naturally from string theory when you work out the math carefully. And here's the kicker. It's not just string theory that predicts something like this. Loop quantum gravity, a completely different approach to quantum gravity developed by physicists like Carlo Rovelli and Lee Smolin, also predicts that singularities get smoothed out by quantum effects. In loop quantum gravity, spacetime itself is quantized, made up of discrete chunks, like pixels in an image. And when you work out what happens at the center of a black hole in this picture, you find that the infinite compression stops at the Planck scale. The collapsing matter bounces back, potentially creating a white hole that erupts into another region of spacetime. Different theories, different mathematical frameworks, same basic conclusion. The singularity isn't real. It's a placeholder for physics we don't yet understand, but which certainly doesn't involve actual infinities. Just when you thought you understood what's going on, let me introduce you to an even deeper puzzle that's been keeping physicists up at night for the past decade: the firewall paradox. In 2012, a group of physicists including Ahmad Almhiri, Donald Meroff, Joseph Polchinski, and James Sully, collectively known as the MPS, published a paper that shocked the theoretical physics community. They showed that the smooth event horizon we've been talking about might not be so smooth after all. In fact, they argued that there might be a literal wall of fire at the event horizon, a firewall of ultra-high energy particles that would instantly incinerate anything trying to cross. Here's the logic. We know from Hawking's work that black holes radiate. As they do, they lose mass and eventually evaporate. Now, quantum mechanics tells us that the Hawking radiation must be correlated with the matter that fell into the black hole. That's how information gets out. But quantum mechanics also tells us that Hawking radiation is created by entangled particle pairs at the horizon, with one particle escaping and one falling in. The problem is that a particle can't be maximally entangled with two different systems at once. That would violate the fundamental rules of quantum mechanics. So either the radiation isn't correlated with the interior, information is destroyed, violating quantum mechanics, or the particle pairs at the horizon aren't entangled, destroying the smooth horizon and creating a firewall, or there's something wrong with our assumptions about how spacetime works. This is the firewall paradox, and it's forced physicists to reconsider everything they thought they knew about black holes. Stephen Hawking himself weighed in before his death in 2018, arguing that the paradox suggested black holes might not even have well-defined interiors in the traditional sense. The most popular resolution to the firewall paradox comes from an idea called black hole complementarity, developed by Leonard Susskind, Laris Thorlacius, and Gerard T. Hooft in the 1990s, but now extended in new ways. The basic idea is that the description of what's inside a black hole and what's outside are complementary descriptions of the same physics, like two sides of a coin. An observer falling into the black hole experiences a smooth horizon and sees an interior, though still no singularity in the quantum picture. But an observer staying outside sees all the information encoded on the event horizon, like a hologram. These aren't two different realities. They're two different valid descriptions of the same reality, and you can never bring them into conflict because you can't be both inside and outside a black hole at the same time. The firewall paradox arises when you try to combine these two complementary descriptions as if they were the same thing. Think of it like this. Imagine you're looking at a coin spinning in the air. At any given moment, you can only see one side heads or tails. Someone on the other side sees the opposite face. Neither of you is wrong, but you can't simultaneously see both faces of the same coin from your single vantage point. Black hole complementarity suggests that the inside and outside of a black hole are related in a similar way. They're complementary perspectives on the same underlying reality, not two separate realities that coexist. This has profound implications for the singularity question. If the interior and exterior are complementary descriptions, and the exterior description is complete, everything is encoded on the horizon, then the interior description, including any singularity, might be redundant, a kind of mathematical fiction we use for convenience, but which doesn't correspond to independently existing physics. In other words, asking what's at the center of the black hole might be like asking what's at the edge of the Earth before we understood the Earth was round. The question assumes a structure, a center, an edge that doesn't actually exist in reality. Okay, so if the singularity isn't real, what is at the center of a black hole? This is the question I promised to answer, and now we finally have the pieces in place to tackle it. The honest answer, the answer that represents the current state of our understanding, is that we don't know with certainty. But we have some very good ideas, and they all point in the same direction. There's something there, something extremely dense and exotic, but it's finite, not infinite. The physics doesn't break down. It just becomes quantum mechanical in a way we're still working to understand fully. Here's what we can say with confidence. At the scales we're talking about, the Planck length of about 10 to 35 meter spacetime itself becomes granular, quantum, uncertain. The smooth geometry that general relativity describes is an approximation that works beautifully at large scales, but fails at these tiny distances. Just like water looks continuous until you zoom in close enough to see individual molecules. In this quantum realm, the notion of a specific point in spacetime becomes fuzzy. You can't localize something to an infinitely precise position. Quantum uncertainty prevents it. So the idea of all the mass being at a single point doesn't even make sense quantum mechanically. The mass is smeared out over a small but finite region, probably on the order of the Planck length. What exactly this looks like depends on which approach to quantum gravity you favor. In string theory, as we discussed, it's a fuzzball of tangled strings. In loop quantum gravity, it might be a region of extremely curved, quantized spacetime, possibly bouncing back and forming a white hole. In other approaches, it might be something else entirely, perhaps a Planck star, a hypothetical object where quantum pressure balances gravitational collapse at the Planck density. The key point is this: in every serious quantum gravity approach, the singularity is replaced by something finite and comprehensible, even if exotic. The laws of physics don't break down. Mathematics continues to work. The universe makes sense all the way down. Think about what this means. The singularity was always a kind of intellectual cowardice, a way of saying physics ends here, here be dragons. But nature doesn't work like that. Nature is consistent all the way down to the smallest scales. The singularity was our failure to understand, not a fundamental feature of reality. Here's another way to think about it. Imagine you're a scientist in ancient times trying to understand rainbows. You develop a theory that light from the sun interacts with water droplets in the air. Your theory works great and predicts where rainbows will appear. But when you calculate the intensity of light at the very center of the rainbow, your equations give you infinity. Does this mean there's actually an infinite brightness at the center of every rainbow? Of course not. It means your theory has limits. It's not accounting for something. Maybe the discrete nature of water droplets, or quantum effects, or something else. The infinity is pointing you toward new physics, not describing reality. That's exactly what the singularity is. An infinity in our equations, pointing toward physics we don't yet fully understand, not an actual infinite object in nature. Moreover, recent developments in our understanding of quantum entanglement in spacetime have suggested something even more radical. Spacetime itself might be emergent from quantum entanglement. This idea, championed by physicists like Mark van Raamsdonk and Brian Swingle, suggests that the geometry of spacetime, the very fabric of reality, arises from patterns of quantum entanglement between fundamental degrees of freedom. If this is true, then at the center of a black hole, where quantum effects are maximal and our classical notion of spacetime breaks down, we might not even be able to talk about space and time in the usual way. The question, what's at the center, might be as meaningless as asking, what's north of the North Pole? It's a question that assumes a structure that doesn't exist. This is the cutting edge of theoretical physics right now, and it's where the singularity problem is finally being resolved. Not by finding some exotic object at the center of black holes, but by realizing that our entire framework for thinking about spacetime needs to be updated when quantum effects become important. Now, you might be thinking, this is all fascinating, but why should I care? I'm never going to fall into a black hole. The singularity being real or not real doesn't affect my daily life. What difference does it make? Let me tell you why this matters more than you might think. Because this isn't really a story about black holes. It's a story about the nature of reality, the limits of knowledge, and how we know what we know. And those things affect everything about how you understand your place in the universe. First, Consider what it means that we can think our way to these conclusions. Humans, sitting on a small planet orbiting an ordinary star, using nothing but mathematics and reason, can figure out what's happening at the center of a black hole billions of light years away. We can distinguish between what's real and what's a mathematical artifact. We can push the boundaries of knowledge into realms that no human will ever directly experience. That's extraordinary. That's the power of the human mind. But second, and more importantly, this story teaches us something profound about the relationship between mathematics and reality. For centuries, physicists have used math to describe nature with stunning success. Math works so well that it's tempting to think that if the math says something, it must be real. The singularity is a cautionary tale against this kind of thinking. Just because an equation produces a result doesn't mean that result corresponds to physical reality. Mathematics is a tool, an incredibly powerful tool, but it's not reality itself. It's a map, not the territory. And like any map, it can have errors, blank spots, regions where it stops corresponding to the landscape. This distinction matters in your everyday life more than you might realize. How many times have you seen a study that produces a statistical result, or a computer model that makes a prediction, or an AI that generates an answer, and assumed it must be true because it came from math or computation? The singularity teaches us to be more sophisticated consumers of mathematical results. We need to ask, what are the assumptions? Where does the model break down? What's the difference between what the math says and what reality does? Think about economic models that predict market crashes, or climate models that forecast temperatures, or medical models that calculate risk. These are all mathematical descriptions of reality, and they're useful, but they all have limits, places where they break down, singularities in their own way. Recognizing this doesn't mean abandoning these tools. It means using them wisely, understanding their limits, and being humble about the difference between our models and the truth. There's another, deeper reason this matters to you personally. The singularity represented a kind of cosmic boundary, a place where understanding ends. It was the ultimate unknowable thing, a place where the laws of physics don't apply, where causality breaks down, where even asking questions becomes meaningless. Having such a thing at the heart of black holes was philosophically troubling. It suggested that the universe contains regions of fundamental incomprehensibility, places where reason itself fails. But if quantum gravity is right, if the singularity is just an artifact of our incomplete understanding, then there are no such boundaries. The universe makes sense all the way down. There's no point where physics gives up, no region where chaos reigns. Reality is comprehensible, in principle, at every scale. That's a profoundly optimistic conclusion about the nature of existence. It means that the universe is, fundamentally, knowable. Not that we know everything now, or even that we'll ever know everything, but that there's nothing in nature that is in principle unknowable, no mysteries that are forever beyond the reach of reason. Every time we encounter what looks like a fundamental barrier to understanding, an infinity, a paradox, a contradiction, it's pointing us toward deeper physics, not toward the edge of comprehensibility. Think about what that means for your own life and your own questions. When you encounter something that seems impossibly complex or fundamentally incomprehensible, whether it's quantum mechanics or consciousness or the nature of time, or why people do what they do, the lesson of the singularity is this: the appearance of incomprehensibility is usually a sign of incomplete understanding, not fundamental chaos. Keep pushing. Keep asking questions. The answers might be subtle. They might require new frameworks for thinking, but they're there. This also has implications for how you think about limits in general. The event horizon is real. It's a genuine boundary beyond which certain things can't happen. But the singularity, the supposed infinite endpoint, is not. This teaches us to distinguish between real limits and apparent limits, between boundaries that are fundamental to the nature of things and boundaries that are just artifacts of our current level of understanding. In your own life, how many of the limits you perceive are like event horizons, real boundaries based on fundamental constraints, and how many are like singularities' apparent limits that dissolve when you understand the situation more deeply? The answer to that question can change everything about how you approach challenges. Now, here's where I need to challenge you even further, because everything I've told you so far has been theoretical. You might be thinking, sure, the math suggests the singularity isn't real, but how do we know? How can we possibly test this? Here's what's going to blow your mind. We might actually be able to test it. And some physicists think we already have preliminary evidence that the singularity doesn't exist. Let me explain. When black holes collide and merge, they create ripples in spacetime called gravitational waves. In 2015, the LIGO Observatory made the first direct detection of gravitational waves from colliding black holes, an achievement that earned Rainer Weiss, Barry Barish, and Kip Thorne the 2017 Nobel Prize in Physics. Since then, we've detected dozens more gravitational wave events. Now, here's the thing. The precise waveform of these gravitational waves, the exact pattern of the ripples in spacetime, depends on what's inside the black holes. If there's a singularity, the gravitational waves should have certain characteristics. If there's something else, a fuzzball, a Planck star, or any other quantum structure, the waves might be subtly different. We're not quite at the point where we can definitively distinguish these possibilities yet. Current gravitational wave detectors are sensitive enough to confirm that black holes exist and behave as general relativity predicts on large scales, but not quite sensitive enough to probe the quantum structure at the center. But next-generation detectors, like the Einstein telescope planned for the 2030s, might be able to see these subtle differences. Some physicists have already claimed to see hints in the data. In 2018, a team led by Joe Betty analyzed gravitational wave signals and claimed to see evidence of echoes, secondary, signals that would be produced if the event horizon isn't a perfect one-way membrane, but has some quantum structure. The results are controversial and haven't been confirmed, but they point to how we might empirically distinguish between different models of what's inside a black hole. There's another observational avenue, the supermassive black holes at the centers of galaxies. These monsters, millions or billions of times the mass of our sun, are surrounded by swirling disks of matter called accretion disks. The behavior of these accretion disks, how they shine, how they vary over time, how they launch jets of particles at near light speed, depends on the detailed properties of the black hole. Recent observations with X-ray telescopes have shown some peculiar behaviors in these systems that don't quite match what we'd expect. If the black holes had simple, smooth event horizons with classical singularities inside. Again, the data is tentative and debated, but it's suggestive. We might be seeing the first observational hints that quantum effects matter even at the event, horizons of supermassive black holes. But here's the most important point. Whether or not we can currently test the difference, the fact that different quantum gravity theories make different predictions about what's at the center means this is a scientific question, not just a philosophical one. The singularity versus fuzzball versus Planck star debate isn't angels on pinhead speculation. It's physics, with potentially observable consequences. And that brings us to perhaps the most important lesson of this entire journey. The frontier between what we know and what we don't know is not a wall. It's a membrane constantly being pushed forward by human curiosity and ingenuity. 20 years ago, the idea of photographing a black hole's event horizon seemed impossible. Now we've done it. 20 years ago, detecting gravitational waves was barely feasible. Now it's routine. 20 years from now, we might have direct observational evidence about the quantum structure at the center of black holes. The singularity is already dead as a theoretical concept in the minds of most physicists working on quantum gravity. It's just a matter of time before observations confirm what the mathematics already tells us. There's something at the center of a black hole, but it's not infinite. It's not where physics breaks down, and it's not beyond understanding. To really understand why the singularity can't be real, we need to talk about the Planck scale, named after Max Planck, one of the founders of quantum mechanics. This is where things get truly mind-bending, because we're going to discuss the limits of space and time themselves. The Planck length is approximately 1.6 times 10 to 35 meters. To put that in perspective, if an atom were magnified to the size of the observable universe, the Planck length would be about the size of a tree on Earth. It's incomprehensibly small. But it's not just small, it's fundamental. It represents the scale at which quantum fluctuations of spacetime itself become important. At the Planck scale, the smooth fabric of spacetime that general relativity describes becomes a seething quantum foam. Spacetime itself fluctuates, creating and destroying tiny virtual black holes, warping and twisting in ways that make the very notion of a smooth geometry meaningless. The physicist John Wheeler, who coined the term black hole, called this quantum foam, and it's one of the most important unsolved puzzles in physics. Here's the crucial insight. Below the Planck length, the concept of distance itself becomes ill-defined. You can't meaningfully talk about two things being closer together than the Planck length because the quantum uncertainty in their positions becomes comparable to the distance between them. Similarly, below the Planck time, about 5.4 times 10 to 44 seconds, the concept of before and after becomes fuzzy. This has direct implications for the singularity. A singularity is supposed to be a point of infinite density, with all the mass compressed to zero size. But if space itself can't be divided into anything smaller than the Planck length, then zero size is meaningless. The smallest something can be is Planck-sized. The highest density something can reach is the Planck density, about 5.1 times yp kilograms per cubic meter. That's unfathomably dense, about 1,097 times denser than an atomic nucleus. But it's finite, not infinite. At the Planck density, quantum effects completely dominate, and the collapse that general relativity predicts must stop. The mathematics that produces the singularity simply doesn't apply anymore. Think of it like this. Imagine you're writing down smaller and smaller numbers. 1, 0.1, 0.01, 0.001, and so on. In pure mathematics, you can continue this forever, approaching zero, but never reaching it. But in reality, if these numbers represent physical distances, you can't go below the Planck length. It's not that there's something stopping you from going smaller. It's that smaller doesn't mean anything anymore. You've reached the limits of what size means in our universe. This is why every approach to quantum gravity string theory, loop quantum gravity, causal set theory, asymptotic safety, all agree that singularities get resolved. They might disagree on what replaces the singularity, but they all agree that infinite density and zero size are unphysical concepts that don't occur in nature. There's something philosophically profound about this. The universe has minimum scales. Reality is quantized, made of discrete chunks at the smallest levels, not infinitely divisible. This means that certain mathematical operations that work fine on paper, like dividing by zero or compressing something to infinite density, simply have no physical meaning. Mathematicians have known for centuries that infinities cause problems in equations. They've developed sophisticated techniques to handle them, remove them, or work around them. But physics is teaching us something different. In the real world, infinities don't just cause problems. They don't exist at all. They're signs that we're pushing our theories beyond their domain of applicability. Roger Penrose, whose singularity theorem we discussed earlier, has himself acknowledged this. In his later work, he's emphasized that his theorems prove that general relativity predicts its own demise. They show exactly where the theory breaks down and must be replaced by something new. The singularities in his theorems are like the here be dragons, warnings on ancient maps, markers of where our current knowledge ends, not descriptions of what's actually there. Now I want to take you somewhere unexpected. We need to talk about consciousness and information. Because they're intimately connected to the black hole singularity question, in ways that will change how you think about reality itself. Here's a strange fact. The laws of physics are time reversible. If you filmed most physical processes and played the film backward, you'd see something that could actually happen according to the laws of physics. A ball bouncing, chemical reactions at the molecular level, even the orbit of planets. All of these look fine running forward or backward in time. But there's one thing that seems to have a direction, an arrow of time: information and entropy. Information, in the physical sense, is about distinguishability, how many yes/no questions you need to ask to completely specify a state. Entropy is roughly a measure of disorder, or more precisely, the number of microscopic states corresponding to a macroscopic state. The second law of thermodynamics says entropy always increases in closed systems. Information gets scrambled, spread out, made inaccessible. But, and this is crucial, it's never destroyed. The information is still there in principle, just hidden in correlations that are too complex to track. Black holes seem to violate this. Throw anything into a black hole, a book, a computer, a person, and from the outside, it seems like all that information vanishes into the singularity. If the singularity were real, if things actually reached it, and the physics actually broke down there, then information would genuinely be destroyed. The universe would have a drain where information could permanently disappear. This bothered physicists for decades. It bothered Stephen Hawking so much that he bet John Preskill, an encyclopedia, that information was destroyed in black holes. In 2004, Hawking conceded the bet. He gave Preskill a baseball encyclopedia, acknowledging that the information paradox likely meant information wasn't destroyed after all. But here's where it gets really interesting. The resolution of the information paradox, the understanding that information is preserved, requires the singularity to not be real. If there's no singular point where physics breaks down, if the interior is described by quantum gravity with sensible, finite physics all the way down, then there's nowhere for information to be destroyed. More than that, the way information is preserved tells us something profound about the nature of reality. The holographic principle, which I mentioned earlier, suggests that all the information about a volume of space can be encoded on the boundary of that volume. For a black hole, this means everything inside is encoded on the event horizon. But the holographic principle isn't just about black holes. It appears to be a general feature of quantum gravity. Any region of space, not just black holes, can have its complete description encoded on its boundary. In a sense, we live in a hologram. Three-dimensional reality, with all its complexity, is fully captured by information on a two-dimensional surface. This is where consciousness comes in. Your consciousness, your subjective experience, is intimately tied to information processing in your brain. The roughly 86 billion neurons in your brain, with their trillions of connections, are processing information, creating patterns, storing, and retrieving memories. Your sense of self, your qualia, your experience of the color red or the taste of coffee, all of this emerges from information processing. If the holographic principle is right, then in some deep sense, the information that makes up your conscious experience could be encoded on a lower dimensional surface. This doesn't mean you're not real, or that consciousness is an illusion. It means that the substrate of reality is information itself, not matter or energy in the traditional sense. The black hole information paradox forced physicists to take information seriously as a fundamental feature of reality, not just an abstract concept. And once you do that, you realize that the singularity as a place where information is destroyed can't exist because it would violate something more fundamental than gravity, the conservation of information. Think about what this means for your own existence. You are a pattern of information, processed and maintained by the matter in your body, but not identical to that matter. The atoms in your body are constantly being replaced. You eat food, you breathe air, you shed skin cells. Over 7 years or so, almost every atom in your body is replaced, but you remain you. Your pattern, your information, persists. This is the same sense in which the singularity can't exist. It would be a place where patterns are destroyed, where information is erased, where continuity is broken. But the universe doesn't allow that. At the deepest level, reality is about information and its preservation. The singularity, as a destroyer of information, has no place in a universe governed by quantum mechanics. Here's where we're going to blow your mind wide open. Everything I've told you so far has been about what's not at the center of a black hole. Now let me tell you about some of the truly wild possibilities for what might actually be there. One of the most intriguing ideas in modern physics is that our entire universe might be inside a black hole. And not just our universe, every black hole might contain a universe. This is called black hole cosmology, or the Smolin hypothesis, named after Lee Smolin, who developed it in the 1990s. Here's the logic. We know that when you look at the universe from the inside during the Big Bang, it looks like it's expanding from a point of infinite density, a singularity. But we've already established that singularities aren't real. So what was the Big Bang really? Some physicists have proposed that it was the interior of a black hole. When a black hole forms in some parent universe, the collapse doesn't lead to a singularity. Instead, it bounces back due to quantum effects, and this bounce creates a new expanding region of spacetime. From the inside, this looks like a Big Bang. From the outside, it looks like a black hole. This would mean our universe is inside a black hole in some larger parent universe. And every black hole in our universe contains another universe. And those universes contain black holes, which contain universes. And so, on an infinite nesting of universes within universes, like cosmic Russian dolls. This is speculative, but it's not crazy speculation. It's based on serious attempts to understand what quantum gravity predicts about the interior of black holes. In loop quantum gravity, for example, the equations suggest exactly this kind of bounce scenario. If this is true, it has staggering implications. It means the singularity, both at the center of black holes and at the Big Bang, was never real. Both are just the same phenomenon viewed from different perspectives. The creation of a new universe that looks like expansion from the inside and looks like a black hole from the outside. But wait, there's more. Some versions of string theory suggest something even stranger. In string theory, there can be regions where the geometry is so curved and quantum that it becomes fundamentally ambiguous. What's inside and what's outside? Two different observers could give completely different, but equally valid, descriptions of the same space-time region. This is related to something called E=EPR, a conjecture by Juan Maldacena and Leonard Susskind. ER stands for Einstein-Rosen-Bridges wormholes. EPR stands for Einstein-Podolsky-Rosen pairs, quantum entanglement. The conjecture says these are the same thing. Quantum entanglement between particles is actually a tiny wormhole connecting them through space. If this is right, then the interior of a black hole might not be a separate region of space at all. It might be connected to other regions, possibly even other black holes, through quantum entanglement. The geometry of space would be fundamentally quantum and ambiguous, with no clear answer to what's at the center, because the question assumes a classical, well-defined geometry that doesn't exist at this scale. Think about what this means. We've gone from, there's an infinite point at the center, to, there might not even be, well-defined center at all. The interior of a black hole might be a quantum superposition of different geometric states, or it might be topologically connected to other regions of space-time through wormholes, or it might be a new universe, or it might be something we haven't even imagined yet. The one thing it definitely isn't is a singularity. The mathematics is clear on this, even if the details of what replaces it are still being worked out. Here's another mind-bending possibility. Some physicists think that space and time themselves are emergent. They arise from something more fundamental, like quantum entanglement or information. If this is true, then at the center of a black hole, where gravity is strongest and quantum effects dominate, space and time might dissolve into this more fundamental substrate. Asking, what's at the center, would be like asking, what's at the north pole of a circle? The question assumes space has a structure: poles, centers, edges, that it simply doesn't have. At the Planck scale, inside a black hole, space might not exist in the way we normally think of it. There might be quantum information, entanglement, correlations, but not space and time as we know them. This is the frontier of physics right now. We're grappling with the possibility that space and time are not fundamental features of reality, but emergent phenomena that break down under extreme conditions. The black hole interior is one of the few places in nature where we can actually test these ideas, even if only theoretically for now. Now, I can hear some of you thinking, this is all fascinating, but does it matter? We've spent nearly 2.5 hours talking about something that happens in regions of space humans will never visit, dealing with physics at scales we can never directly observe. What's the point? Let me tell you about the practical implications of this research, because they're more profound than you might imagine. First, the mathematics developed to understand black holes has found applications in areas you'd never expect. The ADC-CFT correspondence, a mathematical relationship discovered by Juan Maldacena in 1997 while studying black holes in string theory, has been used to understand everything from superconductors to quark-gluon plasmas to the behavior of electrons in strange materials. The holographic principle has inspired new approaches to quantum computing and quantum error correction. If information can be encoded on lower dimensional surfaces, maybe we can build more efficient quantum computers by exploiting this principle. The techniques developed to handle the singularity problem renormalization, effective field theory, the study of infinities and equations, are now standard tools across all of physics. They're used in particle physics, condensed matter physics, even in understanding phase transitions in everyday materials. But more than specific applications, this research has taught us how to think about limits and boundaries. In engineering, in computer science, in any field that uses mathematical modeling, you encounter the same problem. Equations that work beautifully in most circumstances, but break down, produce infinities or nonsense in extreme cases. This mindset has revolutionized how we approach problems in machine learning and AI. Neural networks, for example, can encounter singularities during training places where the gradient becomes infinite or the loss function blows up. Understanding how to regularize these singularities, how to recognize when they're pointing toward deeper structure in the problem, comes directly from lessons learned in theoretical physics. The information paradox and its resolution have also had practical implications. The understanding that information is preserved, even in extreme circumstances, has influenced cryptography and information security. If black holes can't destroy information, then there are fundamental limits to how completely information can be erased, limits that matter for everything from data, security to privacy to the fundamental limits of computation. There's also a broader cultural impact. A resolution of the singularity problem is a victory for reason and comprehensibility. It says that the universe doesn't contain regions of fundamental chaos or incomprehensibility. Every time we encounter what looks like a wall in infinity, a breakdown of physics, it turns out to be a doorway to deeper understanding. This is profoundly relevant to how we approach problems in society, in technology, in our personal lives. When you encounter something that seems impossible to understand or predict, whether it's the behavior of markets, the dynamics of social systems, the complexity of ecosystems, the lesson from black holes is that apparent incomprehensibility is usually a sign of incomplete models, not fundamental chaos. The universe is comprehensible. Reality makes sense. Physics works all the way down. These aren't just abstract philosophical points. They're practical guides to how we should approach complex problems. Don't give up when things seem infinitely complicated. Don't accept it's just random or it's fundamentally unpredictable. Look for the deeper principles, the conserved quantities, the symmetries that remain valid even in extreme cases. We need to talk about the mathematics of infinities and how physics learned to handle them, because this is really the heart of why the singularity isn't real. In mathematics, infinity is a tricky concept. There are different sizes of infinity, and mathematician Georg Cantor proved this in the 19th century. There's the infinity of counting numbers, 1, 2, 3. The infinity of real numbers, including all decimals, and even larger infinities beyond that. Infinity can be rigorously defined and manipulated in pure mathematics. In the early days of quantum field theory, the theory that combines quantum mechanics with special relativity to describe particles and forces, physicists were plagued by infinities. Every calculation seemed to produce infinite results. Energy levels were infinite. Interaction probabilities were infinite. The theory seemed to be telling them nonsense. Renormalization is a systematic way to identify and remove these infinities, replacing them with finite quantities that can be measured experimentally. It works beautifully. Quantum electrodynamics, the quantum field theory of light and electrons, has been tested to absurd precision predictions match experiments to better than 1 part in a billion in some cases. The key insight is that infinities in equations aren't predictions, they're warnings. They're the theory waving a red flag and saying, I don't know what happens at this scale. You need a more fundamental theory. When you see an infinity, you don't accept it as describing reality. You zoom in, find the new physics that operates at that scale, and use that to get finite, meaningful answers. This is exactly what's happening with the singularity. General relativity produces infinities at the center of black holes. But these aren't real. They're general relativity's way of saying, I don't know what happens here. You need quantum gravity. When you apply quantum gravity, or at least our best guesses at what quantum gravity looks like, the infinities disappear. You get finite quantities. The physics works. General relativity is the effective theory that describes gravity at large scales. It works perfectly for everything from GPS satellites to gravitational waves from colliding black holes. But it has a limited domain of validity. It breaks down at the Planck scale. Quantum gravity, whatever it turns out to be, is the more fundamental theory that works at all scales. And in quantum gravity, there are no singularities. Here's an analogy. Imagine you're describing the ocean using fluid dynamics. At large scales, water acts like a continuous fluid, and your equations work great. But if you tried to use those same equations to describe what happens at molecular scales, you'd get nonsense infinities, discontinuities, paradoxes. Does this mean the ocean contains singularities? Of course not. It means you need a different theory of molecular dynamics to describe what happens at that scale. What's profound about this is that it tells us something deep about the nature of scientific theories. No theory is final. Every theory has limits. But those limits aren't failures, they're features. They point you toward the next level of understanding. The singularity isn't physics failing. It's physics working exactly as it should, showing us where to look for deeper truth. There's one more piece of the puzzle we need to discuss, and it's going to tie everything together in a beautiful way. The entropy of black holes and what it tells us about the nature of reality itself. In 1970, a young graduate student named Jacob Bekenstein had a crazy idea. He was thinking about the second law of thermodynamics, the law that says entropy always increases. He wondered, what happens if you throw something with entropy into a black hole? The entropy would seem to disappear from the universe, violating the second law. Bekenstein proposed something radical. Black holes must have entropy. Specifically, the entropy of a black hole should be proportional to the area of its event horizon. This was shocking, because entropy is usually proportional to volume. The amount of entropy in a box of gas depends on the size of the box. But Bekenstein was saying that for black holes, entropy depends on surface area, not volume. The formula is beautifully simple. S equals A, 4 p squared, where S is the entropy, A is the area of the event horizon, and P is the Planck length. This is now called the Bekenstein-Hawking entropy, and it's one of the most important results in theoretical physics. But here's what's mind-blowing. Entropy is fundamentally about information. In statistical mechanics, entropy measures the number of microscopic states that correspond to a macroscopic state. In other words, how much information you'd need to completely specify the system. The Bekenstein-Hawking formula is telling us that the information content of a black hole is encoded on its surface, not in its volume. This was the first hint of the holographic principle. If the maximum entropy, and therefore maximum information, that can fit in a region of space is proportional to the area of the boundary, not the volume, then in some deep sense, the information about the volume is fully encoded on the surface. Moreover, when Hawking and others calculated the microstates, the specific quantum configurations corresponding to the Bekenstein-Hawking entropy, they found something remarkable. In string theory, you can count the microstates exactly for certain special black holes. The count matches the Bekenstein-Hawking formula precisely. This is one of string theory's greatest successes. It reproduces a result from general relativity using completely different mathematics. But here's the crucial point. Those microstates are configurations of strings and brane extended objects, not point particles. They're spread out over the region near the event horizon. There's no singularity in these configurations. The entropy comes from the quantum states of these extended objects, not from some infinite point at the center. This is profound. The entropy, which is an observable quantity, at least in principle, it affects the temperature of Hawking radiation, is telling us directly that the interior of a black hole is described by quantum states distributed near the horizon, not by a classical singularity at the center. There's another implication. The Bekenstein-Hawking entropy puts an upper limit on how much information can fit in a given region of space. This limit is much smaller than you naively think. For a region the size of your room, the maximum entropy is determined by the area of the walls, ceiling, and floor, and it's vastly less than you could fit if you could use the entire volume. This means the universe is more efficient at storing information than we'd expect from everyday experience. It also means there's a fundamental graininess to reality at the Planck scale. You can't subdivide space infinitely to store infinite information. The singularity, as a point of infinite information density, violates these fundamental limits. We're nearing the end of our journey, and I want to step back and help you see how all of this fits together into a new way of understanding reality. For centuries, humans have been on a quest to understand the fundamental nature of the universe. We've peeled back layer after layer, discovering that matter is made of molecules, molecules of atoms, atoms of particles, and particles of... Well, we're still working on that. Maybe strings, maybe quantum fields, maybe something else. What we're learning is that reality is fundamentally quantum and fundamentally informational. Space and time, which seems so real and fundamental to our everyday experience, might be emergent phenomena like temperature or pressure, which seem fundamental but are actually statistical averages over microscopic motion. At the deepest level, reality might be made of quantum information, patterns of correlation and entanglement, with space and time arising from these patterns the way a hologram creates a 3D image from 2D information. The black hole, that most extreme object in the universe, is our laboratory for testing these ideas. And the singularity? It's the placeholder for everything we don't yet understand about this quantum informational reality. As we fill in our understanding, as we develop quantum gravity and test it against observations, the singularity fades away, replaced by something finite, comprehensible, and beautiful. Think about what this means for your place in the universe. You are a pattern of quantum information, processed by the matter in your brain, giving rise to consciousness and experience. You're made of the same stuff as black holes, quantum fields, space-time, information. The laws that govern the most extreme objects in the cosmos are the same laws that govern you. When physicists say they're trying to understand what's at the center of a black hole, they're really asking, What is the fundamental nature of reality? What remains when you strip away all the approximations, all the effective theories, and get down to the bedrock truth? And the answer, increasingly, is information, preserved and transformed according to quantum rules, giving rise to spacetime itself. The singularity represented a kind of intellectual defeat, a place where we threw up our hands and said physics ends here. But we've learned that physics doesn't end. It transforms, it evolves, it reveals new layers, but it never stops working. There's no place in the universe where the rules break down completely. And that means you, with your human brain and your capacity for reason, can grasp the fundamental nature of reality. You might need mathematical tools, experimental data, centuries of accumulated wisdom, but it's graspable. The universe makes sense. Let me bring everything together now and show you the bigger picture that's been emerging throughout this entire journey. We started with a simple claim. The black hole is real, but the singularity is not. Now you understand why this is true. The event horizon is real, a geometric property of spacetime, verified by observations of gravitational waves, by images from the Event Horizon Telescope, by decades of watching stars orbit Sagittarius A star. But the singularity, that supposed point of infinite density and infinite curvature at the center, is a mathematical artifact, a sign that our classical theory of gravity breaks down and must be replaced by quantum gravity. Every approach to quantum gravity string theory with its fuzzballs, loop quantum gravity with its bouncing cosmologies, and every other serious attempt agrees that singularities are smoothed out by quantum effects at the Planck scale. They disagree on the details, but they agree on the fundamental point. Infinite densities don't exist in nature. The information paradox requires this. If information is conserved and quantum mechanics demands that it is, then it can't be destroyed at a singularity. The holographic principle suggests that information is encoded on the event horizon, making the interior redundant. The Bekenstein-Hawking entropy tells us the information content is finite and proportional to surface area, not volume. All the evidence theoretical, mathematical, and increasingly observational points in the same direction. The singularity was a ghost, a placeholder for our ignorance, and now we're exercising it with better understanding. This principle applies everywhere. In the early universe, we used to think there was a singularity at the Big Bang, an infinitely dense point where the universe began. But now we understand that quantum effects must have smoothed this out too. There was no moment of infinite density, no true beginning from nothing. Instead, there was likely a quantum bounce or transition from a previous state. The same principle applies to other infinities in physics. When quantum field theory produces infinite results, renormalization removes them by recognizing that the theory is incomplete at short distances. When calculations diverge, it's a sign you need better approximations or a more fundamental theory. The lesson is universal. The universe is finite and comprehensible at all scales. Infinities are artifacts of our descriptions, not features of reality. Every time we've encountered an apparent infinity in nature and investigated carefully, it's turned out to be removable, an approximation that breaks down, a sign of incomplete understanding. This has profound implications for how we think about limits in general. What other infinities in our thinking are really just artifacts of incomplete understanding? When we say something is infinitely complex or infinitely difficult, are we making the same mistake as assuming the singularity is real? You can see this same pattern in the history of science. Newton's gravity seemed complete until Mercury's orbit showed tiny deviations. Einstein's relativity resolved those deviations, but produces its own infinities. Quantum gravity will resolve those infinities, but will likely have its own domain of validity. Its theories all the way down, each more fundamental than the last, but never reaching a final, complete description. And that's okay. That's not a bug, it's a feature. It means there's always more to discover, always deeper truths to uncover. The singularity, by being impossible, by breaking all the rules, was actually one of the most valuable things in physics. It showed us exactly where to look for new physics. We've been on a journey together for 3.5 hours now. We started with a provocative claim that seemed almost contradictory. The black hole is real, but the singularity is not. Now you understand not just why this is true, but why it matters. Black holes are real. They exist. We've photographed their event horizons, detected their gravitational waves, watched stars orbit around them. They're among the most extreme, most fascinating objects in the cosmos. But at their centers, there are no infinite points, no places where physics breaks down, no fundamental mysteries that are forever beyond understanding. The singularity was always a lie we told ourselves, a confession of ignorance dressed up as a fact. And recognizing this, really understanding it, changes how you see reality. The universe doesn't contain regions of fundamental incomprehensibility. Physics works all the way down. Reality makes sense. When you look up at the night sky and think about the black holes out there, the stellar mass ones scattered through the galaxy, the supermassive ones at galactic centers, the hypothetical primordial ones from the early universe, you can now understand them differently. They're not cosmic drains where reality ends. They're laboratories of extreme physics, places where quantum gravity becomes important, windows into the deepest nature of reality. The universe is comprehensible. That's the ultimate message of the singularities on reality. When we encounter apparent incomprehensibility, it's a sign of incomplete understanding, not fundamental chaos. Keep asking questions. Keep pushing for deeper explanations. The answers are there. Thank you for taking this journey with me. If this changed how you see reality, if you'll never think about black holes, or infinity, or the nature of existence the same way again, then hit that subscribe button. Share this with someone who needs their mind blown, and drop a comment telling me what aspect shocked you most. The universe is vast and weird and wonderful, but it's yours to understand. Never stop asking why.